Welcome to the ninth lecture from chapter 8. We are talking about chain delays. In last lecture, we talked about the chain of NOT gates, where the NOT gates were the scaling factors of NOT gates were powers of 2. Today, we'll find out the optimum value of the scaling factor S. Now, we will keep it in general instead of 2. Instead of 2, we have S here. And we'll find the optimum value of S for which the chain delay is minimum. So if we have S as the increasing scaling factor, the second NOT gate will have a scaling factor S, and the next will have a scaling factor S squared, and then the last would be having a scaling factor S to the n minus 1, which will be driving a CL, which is equal to S to the n times the minimum capacitance, where the minimum capacitance, the input capacitance of this NOT gate with scaling factor 1. So let's do a bit mathematics to find the optimum value of S for which the chain delay is minimum. Right, this is our starting point. CL is S to the n, say minimum, or we can write it as CL over C minimum is equal to S to the n, taking C minimum on the other side. Now we need to compute log on both sides, and log S would be log of CL over C minimum, or n can be written as log of CL over C minimum over log of S. This is a very important expression. And in earlier lectures, we have studied that for a chain, the time delay T sub D, T sub D is equal to the sum of all the gates. Here we have n gates times m to the n T sub I, the sum of all the delays caused by these individual gates. Right, and any Ti or T, we already know that the delay, either it is rise time delay or fall time delay, is proportional to the tau. If it is rise time delay, it is directly proportional to the rise time tau, and if it is fall time delay, it's proportional to the fall time tau. But tau is a product of R and C, already know that. So instead of T, tau D, TD, tau D would be written as tau I. So instead of T, D, you can write it tau D, and the summation remains summation, and Ti becomes tau I. Which means it can be further written as tau 1 plus tau 2 plus tau 3 plus tau n. Where tau 1 is the expression tau t, can be rewritten here as tau 1 is the resistance times the capacitance. The resistance of this gate times the capacitance it has to drive, which comes from this gate, the following gate. So if it is R, so the input capacitance, because it has a scaling factor S, would be S times C. Instead of being C, it would be S times C, because this gate is driving another gate whose scaling factor is S. Plus, for this next gate, its resistance would be R over S, because its own scaling factor is S, and it is driving another gate whose scaling factor is S squared times C. Plus, for this is R over S squared, and it is driving another gate whose scaling factor is S cube times C, where C is the C minimum, plus for the last gate n minus 1 gate, it's n minus 1. This is R over S to the n minus 1 times it is driving a capacitance whose value is S to the n times C, C minimum. For short, we write it only C. So, what we are left with is a very interesting expression, square. So, we are left with RSC here and here RSC. They are all the same. Plus RSC. How many times? Because we have n gates, n times. Dot is n times R times S times C. And earlier in the lecture, we derived an expression for n is equal to log of CL over C over log of S. If we put the value of n here, we can find an expression for tau d. So the new tau d becomes, putting this value of n here, log of CL over C over log of S times R times S times C.